Guys, Mr. O'Sullivan here. Hey, we're going to go over that problem AB number 1. That was a homework problem. And first off, a quick shout out to Jeff Osborne, who's a AP calculus teacher at Central Columbia High School in Bloomsburg, Pennsylvania. And he was the gentleman who came up with this problem. It's a great problem because gives you a chance to kind of practice a problem that's going to be 25 minutes long and could probably represent that first problem that you might look at on the actual exam on May 12th. So kind of good for us to get used to practicing a little bit longer free response problem than just one with like 3 or 4 parts to it. All right, so let's go ahead and dive into this one. And it's a particle motion problem. So we've got a particle is moving along the x-axis with a velocity function v at t equal 3t squared minus 8t plus 4. Position of the particle is given by the function x at t, and then we're given an initial condition. It's known that x at 0 is equal to 7. So again, I want to make sure I kind of highlight that so I don't forget about it. So we know that the position of the particle at time 0 is at 7, positive 7 on the x-axis. Okay, so part A says on the interval from 0 to 4. Okay, so again, we're just looking at the interval from 0 to 4. When is the particle moving to the right? Give a reason for your answer. Okay, well, we know what's going to indicate the particle is moving to the right is when velocity is positive. So I'm just going to say particle moving to the right when v at t is greater than 0. Okay, well, when do we know, or how do we find the interval where velocity is greater than 0? Well, again, we're given the velocity function a couple ways. We can use our calculator. We could use it, plug that in as y1, and then just look to see where the function is above the x-axis. That's going to be the interval where velocity is positive. Or algebraically, we could look at this function and factor it. Now, it's a little challenging because that lead coefficient is not 1, it's a 3, but it still is going to factor. And I'm going to give a credit to a good teacher buddy of mine, Wes Cox, that I call the Cox method of factoring a quadratic when this lead coefficient is something other than 1. So what you can do is take the 3 and the constant, multiply those together, you get 12. Now what we're looking for are factors of 12 that are going to add up to that middle coefficient, -8. So it looks like it's going to be 2, -6. And what we're going to do is we're going to split this middle term into -2t and -6t. And just bring the constant down. Bring the squared term down. So we have 3t squared minus 2t minus 6t plus 4. And now we're just going to factor by grouping. So in this first term, we can pull out a, looks like we just have a common factor of t. So we have t times 3t minus 2. And then in the second two factors, or second two terms, we can factor out, looks like a -2. When we factor out a -2, the other factor is going to be 3t minus 2. Now that's the check. We need to make sure that those two factors are the same. Then we can factor again. We're going to get t minus 2 times 3t minus 2. Then if we set that equal to 0, we can see that t is going to be equal to either positive 2/3 or positive 2. And again, if it's helpful to look at that just kind of graphically, that's given us our t-intercepts in this case. So really, our function, if we were to graph v at t, that's the t-axis, and so that's our function v at t, we're going to see that the t-intercepts are 2/3 and 2, which is going to indicate that the velocity is positive for t-values less than 2/3 and for t-values greater than 2. So how I'm going to finish this, I'm going to say the particle is moving to the right when velocity is positive, and v of t is positive on the interval. And again, we're looking specifically from 0 to 4, so we could say from 0 to 2/3, and then also on the interval from 2 to 4. Okay, so there's part A, that's the interval where our particle is moving to the right. Part B, thank you very much. Same interval. When is the particle moving to the left? Give a reason for your answer. Well, we've already done the heavy lifting for that one. Particle is moving left when v of t is negative. V of t is negative on the interval, and then now I'm looking at the interval from 2/3 to 2. So I'm looking at that portion right there. So that's going to be 2/3 to 2. So in that t interval, that's when my particle is moving to the left. Okay. Part C. Part C, couple ways you can go on this one. Part C, you could say, well, gee, they're asking me to find the average acceleration of the particle on the time interval 0 to 4. Well, I can either go this way and find the average value of a function, which would be, that's my 1 over b minus a times the definite integral from a to b of that function I'm asked to find the average of, in this case, acceleration. So I could set it up like this, 1 over 4 minus 0 times the definite integral from 0 to 4 of acceleration, which is the derivative, right, of velocity. So that's one way I could set it up. I could work it out that way. Or, this might be a little bit easier, I could realize that, hey, you know what? Average acceleration is the same thing as the average rate of change of velocity. And so really, this might be the easiest way to think of it in terms of that. The average rate of change of velocity on that interval from 0 to 4 is going to be v at 4 minus v at 0 over 4 minus 0. So now I just need to know, I can't leave my answer like that. It's not numeric. I have to find v at 4. So I go back to my velocity function, 3t squared minus 8t plus 4. So v at 4 is going to be 3 times 4 squared minus 8 times 4 plus 4. And then v at 0, actually that's going to be a little bit easier. I can just see right off, that's just going to be 4. So if I want, I could just substitute v at 4. I can just put in that expression. I'd have to do any kind of simplification. 3 times 4 squared minus 8 times 4 plus 4, and then minus v at 0, which is 4, all over 4 minus 0. And that's going to be my average acceleration. Now, if you think about it, this first way, setting it up as the average value of the acceleration function, we're going to get the exact same answer, aren't we? Because the first thing we're going to do is find the antiderivative of acceleration, which is velocity, plug in our upper bound minus plug in our lower bound of 0. So we're going to get v at 4 minus v at 0, looks like that. And then the 1 over 4 minus 0, that's how we get the denominator. So we can go either way on that. Okay. Part D, find a at 1, the acceleration of the particle at time t equals 1. All right, well, if velocity, v of t is equal to 3t squared minus 8t plus 4, and I'm looking for acceleration, I'm looking for the derivative, so v prime at t, just straight up power rule, that's going to be 6t minus 8. Then I want v prime at 1, so that's just going to be 6 times 1 minus 8. I could stop right there, which is also negative 2. Okay. Part E, is the speed of the particle increasing or decreasing at t equals 1? Okay, now again, this is one thing that we just kind of have to know sort of cold. If they're asking us for the speed of the particle, we just want to remember speed is increasing when speed is increasing. Let me just put it right under. When A at t and V at t have the same signs. So for that particular time value, if acceleration and velocity both have the same sign, both negative or both positive, doesn't matter. They both have the same sign, we say that the speed of the particle is increasing. Okay. Well, then obviously, speed is decreasing when A at t and V at t have different signs. Okay, well, we just found V prime at t would be the same as A acceleration. And so we found that A at 1 is negative. Is negative 2, right? So it's just negative. And so what we have to do is we have to check what is V at 1. Okay, there's velocity right here. That's going to be 3 times 1 squared minus 8 times 1 plus 4. That's going to be 3 minus 8 plus 4. Looks like that's going to be negative 1, which is a negative number. So therefore, acceleration at time 1 is negative. Velocity at time 1 is negative. The signs are the same. So therefore, speed is increasing at t equals 1. Okay, that's it. I got to look again. If it's speed, I have to compare the signs of both velocity and acceleration at that particular time. Okay. Find the position function x at t for the particle. Okay, 2 ways I can do this one. And I could set this up and I could treat it as a indefinite integral. Yeah, or I could treat it as a definite integral. I'm going to show you both. You pick the one that you can wrap your brain around. Okay, as an indefinite integral, I know that position is going to be equal to the integral of velocity. And I also have to remember that I'm given this initial condition, x at 0 is equal to 7. Okay, so the first thing I'm going to do is I'm going to take my velocity function, which is the 3t squared minus 8t plus 4 dt, and I'm going to integrate that. So I'm going to get x at t is equal to 3t to the third over 3 minus 8t squared over 2, should simplify down to 4 minus 4t squared plus 4t plus c, because that's an indefinite integral. Okay, now what I have to do is I have to plug in my initial condition, x at 0 is equal to 7. So that is going to be, I'm just going to rewrite this, x at t is equal to t cubed minus 4t squared plus 4t plus c. Substitute in my initial condition, that's going to be 7 is equal to c. That's going to go in right there, and then that is my position function x at t. Value of my constant of integration is 7. So t cubed minus 4t squared plus 4t plus 7. Okay. as a definite integral. I'm just going to kind of set it up and then let you kind of run with it. I could set it up and say that x of t is equal to x at 0 plus the definite integral. Now my lower bound has to match that t value, so I'm going to set my lower bound of 0. And then my upper bound I'm going to leave as my variable t. And then I'm just dropping in the velocity function. I'm just going to use a different variable in my velocity function other than t. So I'm just going to say about 3a squared minus 8a plus 4 dA, not dt, dA. Okay. And then I can just x of t is equal to x at 0 is given as 7. And then to evaluate this, plus antiderivative is going to be 3a to the third over 3. Gosh, this seems familiar. Minus 8a squared over 2, 4 plus 4a, and then my lower bounds, 0 and t. When you plug that in, you're going to get the exact same position function that we got, treating it as an indefinite interval. Okay, so either way, we can handle it either method. Okay, part G says use the position function you found in part F to find the values of x at 1, x at 4. All right, well, so we're using x at t, t cubed minus 4t squared plus 4t plus 7. I'm going to find x at 1, 1 cubed minus 4 times 1 squared plus 4 times 1 plus 7. And then x at 4, 4 cubed minus 4 times 4 squared plus 4 times 4 plus 7. Okay, these are both numeric answers. I'm just going to leave them just the way they are. And then part H, find the total distance traveled by the particle on a time interval from 1 to 4. Okay, again, two ways I can do that. One way would be to treat total distance defined as a integral. So the total distance is going to be equal to, on this interval from 1 to 4, it's going to be equal to the definite integral from 1 to 4 of absolute value of my velocity. Okay, if it's just the definite integral from 1 to 4 of velocity, that's going to give me displacement, not total distance. So it's the absolute value of velocity. Okay, that's going to give me total distance. Okay, now, because I'm dealing with the absolute value of velocity, and velocity is negative over some portion of this interval. Remember what the velocity function looked like graphically on that t-axis. That was at 2/3. That's at 2, and we're interested in the interval from 1 to 4. So really, we're like right here. There's 1, and there's 4. So we can see that velocity is negative on this interval right here, and then it changes to positive on that interval right there. So from 1 to 2, it's negative, and then from 2 to 4, it's positive. So what I can do is break this one integral up into two integrals. And I can break, the first integral is going to be from 1 to 2, where velocity is negative. So 1 to 2. What I'm going to have to do is I'm going to have to take the negative of velocity. Okay? And then my second integral is just going to be the remainder of the interval from 2 to 4, lower bound of 2, upper bound of 4. This is where velocity is positive, so my integrand is just going to be via t dt. Okay, so again, algebraically, I could do that. I could just drop in the velocity functions there, FTC part 1, come up with both of those and get my answer. The second way you could do this one would be do a quick table and look at the position, the values of the position function at 1 and 4, my endpoints, but then I also have to check where my position, where my particle changes direction. So I also need to look at the position at time 2. Okay, well, I've already done the lion's share of the work. X at 1 is equal to, well, I didn't simplify that, but if I do simplify that, I'm going to get, that's going to be 8. And if I look at X at 4, that's going to be 23. And then what I have to find is I got to find X at 2. So I'm going to do X at 2 is equal to, and I'm looking at my position function, 2 cubed minus 4 times 2 squared plus 4 times 2 plus 7. And if we work that all out, we're going to get 8 plus 8 minus 16 plus 7. 8 and 8 is 16 minus 16, so that's going to work out to be 7. Now what I can look at is I can look at the change in position. So from 8 to 7, that's a decrease of 1. And from 7 to 23, rather, that's an increase of 16. If I just combine those two, that's going to be 15, but that's going to be the displacement. From t equals 1 to t equals 4. That's displacement. So what I have to do is I have to take the absolute value of -1 is 1. Absolute value of 16 is 16. Add those two together, and 17, that is my total distance over the interval 1 to 4. Okay? All right, guys. Hope that helps. Thanks.